Greetings to my students and to subscribers to my channels, Architectural Structures Aficionados. Thank you for joining me. This is Deborah Oakley at the University of Nevada, Las Vegas School of Architecture. Today I'm going to be looking at rigid shell structures and how we can model these in Rhinoceros 3D software. Rigid shells are some of the most elegant and efficient types of structures that we can develop under compression. They're surface structures such as this four-square hyperbolic paraboloid membrane that formerly existed in downtown Denver, Colorado. This was demolished about 2004. This is by the famous engineer Anton Tedesco. So rigid shells such as this chapel at the St. Louis Priory Abbey have some of the thinnest profile that you can possibly have under compression. You can see the edge here. This is only a couple of inches thick. This is a paraboloid shape that is extruded and rotated and stacked and creating this intersecting set of spaces that generates a really wonderful interior environment here. Or such as this project. This is a library for the University of Basel in Switzerland. It has these petal shapes that again rotate around a center. There's the interior space. Or another example are these inverted umbrellas at the Student Center at the University of California at Berkeley. This goes back to the 1960s. What I like about this project is how the umbrella column lines have been offset by 1/2 of a bay for every other column line, and that results in a offset of the valley line, and so we get these diamond shapes that emit light inside of here. Now, before I go any further, open up Rhino here, I want to make that one thing perfectly clear here, is that these shapes are not arbitrary. They do follow specific rules. If you're going to have a thin shell structure, it has to be a funicular structure. That is, that it is under compression without any bending forces. So, for example, if I go into my front view here and simply draw an arc, we'll go across here, not any particular shape here. And I'm going to make a copy of this, just Control C and Control V, and move this. And I like to use the gumball here. I'm going to rotate this about the horizontal axis here by 180 degrees. And let's make another copy of those two, Control C, Control V, and then rotate this whole bunch here about the vertical axis 90 degrees. And let's maximize the perspective viewpoint here. And let's move some of these lines here. And I'm just going to join the endpoints. And from these curves, I'm going to use the network surface command to generate a surface. And there we are. We have a surface in Rhino, and you can easily generate any kind of surface. The point here is that this is not a structural surface. In fact, if we were to support this at these points and apply a gravity load, part of this shell would be under compression and part would be under tension, meaning that there would be a transition from tension to compression. And the only way that that can happen is if there is bending. And if you have bending, you do not have a funicular shape. So a true funicular surface would take the form that this would take bounded by those curves, but formed by a soap film. So a good example of that is these soap film studies that were done by the renowned architect engineer Fry Otto, passed away in 2015, winner of the Pritzker Prize shortly after his death. And these explore different boundary conditions, and there's only one shape that these can take. Another example is this one I found online, just random wire connections dipped into soap film. This will be its natural form, and it can only take one particular form. So that's kind of like the underlying underpinning of our whole study here. So I'm going to go ahead and delete that. And let's first off start with some properties of these structures. So I have a couple of cones here drawn inverted, and I have a clipping plane off the edge of the screen here, and I'm going to move this clipping plane through this cone, and this is the classic conic section. You might have learned this in a math class very early on, maybe in high school. As I drag this through here, the clipping plane creates a hyperbola. These two curving shapes here are defined mathematically as a hyperbola. Now if I move this further to the center, and I'm going to rotate this by 90 degrees, and actually I want that to be the other way, so let's change the properties, flip that direction there. What I want to do is drag this down, and I see that now I'm clipping a circle, and this circle will be of varying diameters as I go through here. However, if I rotate this at all, I now have an ellipse. If I continue to rotate this, then and grab on that little handle there, now I have a parabola. So these are the conic sections, the classic conic sections. So let's go ahead and restore that clipping plane to its home location. And let's look at another form here. So the conic sections are the hyperbola, the ellipse, circle, and the parabola. Now I have another form drawn. This is a torus, a donut shape. We draw a torus with the solid command and using torus. Just generate a center point and drag. It's pretty simple. If I bring on my clipping plane once more, what I'm going to do is in a right-hand viewport here, I want to actually move this up above the torus. And I'll go back to my perspective view. And I want to rotate this around by 90 degrees. Nope, I actually want that pointing down, so let's make that 180. Torus has disappeared, and the reason is because it is not being shown because it's clipped. Now, if I clip a little bit, I get another ellipse form. So this is the form that we might see, for example, in this structure, the Beijing National Center for the Performing Arts by the French architect Paul Andreau. So it is a regular form that's generated from a regular object, in this case a torus. So let's reset this clipping plane again, and I'm going to turn off the clipping plane. Let's explore something else with the torus here. Let's go into a top view, and I'm going to draw a rectangle from the center point origin, and not a particular shape here. I'm going to use that rectangle as a trim line for the torus. And go back into perspective view. Trim will project up and down in both directions, and so I'm left with these 4 segments. And so this piece here, let's focus on this particular one right here. I want to see that it is doubly curved. This is an anti-clastic surface. That is, it's an inwardly curved surface. It has curvature in 2 directions. It's actually to inward and outward bowed. We have this upward parabolic shape as well as a hyperbolic shape. We can see the hyperbolic shape if we were to cut a plane through here. So let's create a plane. Go to my top view. And let's move this up and use that as a trimming element. And now I don't need it, so we'll delete it. And we see the hyperbolic shape as well as the parabolic shape. This is a fundamental form that we will see over and over here in this video. So I'm going to go ahead and delete all this. I've got an extra copy of that torus right here. And what I want to do now is look at another way of trimming this. So I'm going to go into a front view. Actually, I want to put this onto the layer for the torus. Whoops, not the lines. Go on to the torus. Okay, the reason I did that is because I have this set with a transparent material. Now, I've turned on this layer here called Trim Lines, and I'm going to use that to carve up the torus again. So I'll start with the bottom line, and I'm going to trim everything down below. And I've got these two inclined lines, and I'm going to trim off everything above. Now, from a top view, I have two additional lines, and I'm going to use those to trim off these edges here. And now turn off that layer Trim Lines, go back to my form, and now I've got another form of a hyperbolic paraboloid. So let's make this actually a surface. I'm going to use offset surface, and we'll do this to the inside. Now these shells are very thin, so this can only be possibly 3 inches maybe thick. So I've got the distance set at 3/10 of a foot. I'm in feet here. And so now I have a shell. And we can see the remarkable similarity that this has with this example. This is the chapel at Cuernavaca, Mexico by Felix Candela, one of his early projects in the 1950s. And it is still in use. So that's pretty neat. So that is another type of way of looking at creating a regular structure. So let's go to the next form I want to look at. This is a hyperboloid form. I'm going to generate this from two circles. And as I drag this, I'm going to tap the Option key and make a copy of the top circle. And then I'm going to scale it in. And by selecting these two circles here, I'm just going to create a lofted surface. And it doesn't look like too much right now, but I have record history turned on. So this circle is the generator of, well, the two circles, but the circle is the generator of the surface. So if I manipulate that surface, circle that is, it will change the surface. So I'm going to rotate this about the blue by 135 degrees, and we get a hyperboloid form. These might look familiar to you. Maybe if I reduce that, let's knock off 45 degrees on that. I'll go backwards, negative 45. That form we've often seen in structures like this, the classic cooling tower that you find at coal-fired and nuclear power plants that used to cool the water that comes from the boiling from the reaction or the coal, and to cool the water and condense it back for recycling. So this is seen architecturally. I'm going to actually lower this time. And we can play with the form. Let's pull this inward and give it that little extra twist. I'm going to add 45 degrees. And maybe widen it just a little bit more. And now we have something that looks like that. Looks like this should be a little bit wider to match that. That is the McDonald Planetarium at St. Louis Science Center. And notice the shape here. We can see the lines that make this up. It's also very similar to the structure by Oscar Niemeyer, the Cathedral at Brasilia, Brazil. So there are two ways of looking at this. This is a lofted form, or if I rebuild this, and let's do this only in the V direction, we can see that if I turn on the isocurves here, It's actually made of straight lines, and that is a fundamental characteristic of hyperbolic paraboloids, that they can be created from straight lines. So now let's go to make some planes. So one of the easiest ways to make a hypar is actually to start with a couple of straight lines. So let's make a line. An arbitrary length here. And make a copy of that line. Now if I loft between those two forms, I get a plane. And just like I did with the hyperboloid, if I take one of the generating curves and rotate it, I get a twisted shape. That is, in fact, a basic hyperbolic paraboloid shape. So another way of thinking about this surface, let's rebuild this. And I'll just keep that as the default there. Maybe reduce it to 20. And I'm going to actually extract those iso curves. And I want the U direction in all of those, so they become objects. So we can see the straight line surface there. This is called a ruled surface. So we can generate this ruled surface also with the sweep command. So maybe I'll delete these guys here and take these two edges here as the rail. And I'm going to do a sweep to rail and use this curve. And you see we generate our surface once again. So it can be swept, it can be lofted. Those are both two ways of doing it. One of the more interactive ways that I really like, though, is to start with a plane. I'm going to start at 0, and we'll go out, let's say, 40 feet on a side. And I'm going to turn on my solid points. So you'll find this under, and actually these are very hard to see, so I'm going to change my display properties here. I have this in rendered mode. I'm going to change my control point size to, let's say, 4, maybe 5, so we can actually see those. And very simply, just grab 2 of these and pull up. And we create our form. And I'm going to, for now, turn off the iso curves so we can see our shape. Now, something I want to point out here with Rhino, notice that it looks kind of jagged. This is actually a display issue. This is actually perfectly smooth. It is not jagged like this. It would be a little bit smoother if we rebuilt it with more iso curves. But what this really is called the display mesh. So if I go to the properties for this, you can see that the object here, it has render mesh settings. It's called render mesh, not display mesh. I can actually change this, click on this, and I have some options that are controlled down here. And the one I want to look at here is the maximum edge length. And you see if I change that to 2 feet, I get a much smoother curve. And so now we've lost all that jaggedness. So this is simply a display issue. Now this can be controlled by object just like I did, or if we go into the mesh panel, or in mesh pull down, go to render mesh properties. The default for this is jagged and faster. This is really to enable a slower computer to not get bogged down with the graphics. But I'm running Rhino on a 4-year-old iMac using Parallels, and it's still quite fine. If you get a very complicated model, it might be an issue, but mostly not. But if I set the custom here, I can go into detail controls and then set that to 2 feet just like I did. Now every object that has surface curvature will be smooth. So let's look at this simple shape here in 3 different ways. I'm going to copy one off to the side on the right and copy another one to the side on the left. First off, I'm going to go to a front view and do a simple contour command in the vertical direction. And I'm going to do those at 2 feet so I don't have too many. And what we see is the surface curvature very clearly displayed. This is a referential image. It really doesn't tell us too much. But that's the same process I'm going to do here on the next one. Actually, I'm going to do something else here. I'm going to rebuild this one first. And I'm going to rebuild it in both directions with 20. Maybe that's a little dense. Let's try 10. And so now I'm going to do the same thing I did before, do a curve from object and extract the isocurves. And I want to do this in both directions and extract all. Those are the straight line generators. These are not structural lines. Because they are straight lines, they don't work with the structural surface. The lines that we actually want, I'm going to get from this one. I'm going to go to a top view. And now I'm going to contour this. And I'm going to do it in both directions. First in this direction. Now, why does this look different? Let's go back to perspective view. Notice the curvature. This last one here, this is your structural surface. We have suspension action in one direction and arching action in the other direction. They work together. In a shell structure, this is what you want. You want double curvature action. So there are fun things that we can do with these kinds of shapes. Let's go ahead and delete these guys here. I'm going to use the filters here. I'm going to filter only curves. That way I don't have to worry about selecting the surface. And by the way, if you don't know this, if you right-click, it will select one or deselect them all. That works for object snaps and for object filters. A lot of people don't use the object filters. It's right down here on the bottom. So what can I do with a hyper like this? Well, let's play around with it. How about if we take this and rotate it about a center point? Let's make it a polar array, rather. And I'm going to make 4 copies and 360 degrees. And we get a structure like this. Now I think, because I have history turned on, if I change one of these, yes, they all change. That's the beautiful thing about history. So learn about record history. So we've got a structure. Okay, and so I'm going to stop there. In the next video, stay tuned. I'll show how we can apply these techniques to creating a couple of Felix Candela's iconic projects. So stay tuned. Thanks.